So, good evening, everyone. We are the Group 1, and we're here to present the construction of ternary phase diagram, which is the activity number 5. So, for the introduction, phase diagrams are crucial tools in material science and engineering for graphically representing the equilibrium relationship between phases in a material system. While binary diagrams, two components, a ternary phase diagrams extend this analysis to three-component system, A, B, and C. To simplify, the three-dimensional composition space construction typically involves holding temperature and pressure constants, creating an isothermal section. These three components composition is then plotted onto a two-dimensional Gibbs equilibrium triangle, which provides a geometric representation for all possible compositions. The ability to accurately construct and interpret this diagram is essential for predicting phase stability, optimizing processing conditions, and engineering novel materials by defining the boundaries and tie lines of single phase and multi phase regions at equilibrium. For the objective, first is to determine the effect of alcohol on the miscibility of camphor and water. Second, to identify the miscible and immiscible regions of the camphor alcohol water system. Third, to construct a ternary phase diagram and plot the binodal curve for the system. For the material used, first is camphor, alcohol, distilled water, burette, test tube stand, ruler, a graphing paper, burette stand, 5 ml bulb pipette pencil, boiling test tube, and pencil.
Next, for schematic diagram, first we have the procedure A. So we prepared 6 different amounts of alcohol in clean dry boiling test tube and 6 different amounts of camphor in a clean dry boiling test tube. Then we mix the camphor and alcohol together. For procedure B, we add distilled water from the burette, then let the distilled water drip into the test tube until turbidity is produced. For procedure C, we calculate the percentage weight over weight of each component in the system when turbidity is produced. And the last procedure is we plot a ternary phase diagram and mark the miscible and immiscible regions.
For the data, we have the camphor, alcohol, and the water. So we repeat it 6 times. For the test tube 1, the camphor is 1.2 grams. In alcohol, 2.3 grams. And for water is 0.7 grams. Then for the total volume, kay giad lang sila tulo. For the test tube 2, 2.6, the alcohol is 3 grams. And water is 1.3 grams. The total is 6.4 grams. For test tube 3, 2.1 grams, 1.7 grams, 0.5 grams, and the total is 4.3 grams. For test tube 4, camphor is 3.05 grams, alcohol is 3.4 grams, and ang water is 0.7 grams. The total volume is 7.15 grams. Then test tube 5, 1.8 for the camphor, 2.6 sa alcohol, 0.7 sa water, and ang total volume is 5.1. And lastly, test tube 6, 2.3 grams for the camphor, 1.7 grams for the alcohol, and 0.5 grams for the water. Ang total niya is 4.5 grams. Then, ang sa percentage, i-explain siya sa calculation.
So for the calculations, for the percentage weight over weight of the camphor, so to calculate the percentage weight over weight of the camphor, weight of the camphor and divided with the total weight of the system multiplied by 100. So for system 1, 1.2 grams over 4.03 grams multiplied by 100 gives us 29.79% weight over weight. For test tube 2, 2.6 grams divided by 6.4 grams multiplied by 100 is equal to 37.68%. For system 3, 2.1 grams divided by 4.3 grams multiplied by 100 gives us 48.8%. For system 4, 3.05 grams divided by 7.15 grams multiplied by 100 gives us 42.66%. For system 5, 1.8 grams divided by 5.1 grams multiplied by 100 gives us 35.26 grams percent. For system 6, 2.3 grams divided by 4.5 grams multiplied by 100 gives us 5.11% weight over weight in comfort. So for the calculation of alcohol with its weight over weight percent, first we need to convert the ml obtained during measurement to grams. So during the experiment, the alcohol used was 80% concentration of ethanol, making the density 0.853 grams per ml. So it was already converted prior to the presentation. So for system 1, 2.13 grams divided by 4.03 grams multiplied by 100 is equals to 53.85%. For system 2, 3 grams divided by 6.4 grams multiplied by 100 is equals to 43.48%. System 3, 1.7 grams divided by 4.3 grams multiplied by 100 is equals to 39.53%. For system 4, 3.54 grams divided by 7.15 grams multiplied by 100 gives us 47.55%. In system 5, 2.6 grams divided by 5.1 grams multiplied by 100 gives us 50.98%. System 6, 1.7 grams divided by 4.5 grams multiplied by 100 is equals to 37.78%. The percentage weight over weight of water, we follow the same formula with weight over water over weight of total system multiplied by 100. The same procedure was done to convert the water from ml to grams using 1 gram 1 gram over ml for its density. So for system 1, 0.7 grams divided by 4.03 grams multiplied by 100 gives us 17.37%. For system 2, 1.3 grams divided by 6.4 grams multiplied by 100 gives us 18.84%. For system 3, 0.5 grams divided by 4.3 grams multiplied by 100 gives us 11.63%. For system 4, 0.7 grams divided by 7.15 grams multiplied by 100 gives us 9.8%. For system 5, 0.7 grams divided by 5.1 grams multiplied by 100 gives us 13.73%. For system 6, 0.5% divided by 4.5 grams, sorry, 0.5 grams divided by 4.5 grams times 100 gives us 11.11%.
So for our ternary phase diagram, as you can see, in system number 1 is plotted in 48% because the camphor is equivalent to 29.79% and our alcohol is 52.85% and our water in system number 1 is 17.37%. That's why the 48% is plotted in one because they are intersected in 48%. So for our system number 2, it is plotted in 56% because our camphor is equivalent to 37.68%. For our alcohol is 43.48% and our water is 18.84%. For our uh, system number 3 is in 62% because our camphor is 48.8 and our percent and our alcohol is 39.53% and our water is 11.63%.
intersected in 62%. So for our system number 4, it is plotted in 51% because 66% in our alcohol is 49.8% and they are intersected. System number 5, it is plotted 35.29. System number 5, it is plotted for is 30. Sorry, for our system number 6, it is plotted in 63% because our camphor is 51.11%, our alcohol is 37.78%, and the water is 11.11%. That's why it is they are intersected in 63%.
Now for the guide questions. What is ternary phase diagram? What is its importance in preparing mixtures? So, as a ternary phase diagram is a triangular plot showing how the phases of the three-component mixture behave at a constant temperature and pressure, illustrating equilibrium compositions and phase regions. Its importance in preparing mixture lies in its ability to predict phase stability, optimize formulation conditions for stable emulsions or drugs, and help design separation processes by visualizing component interactions and phase boundaries. Number 2, how to do the plotting of ternary phase diagram. So to plot a ternary phase diagram, define your three components. So our experiment here, we have the three components, which is the alcohol, the camphor, and water. Now normalize your percentages so they sum to 100%. And then plot the data points on the triangular diagram by drawing lines from the percentage for the percentage on the side corresponding to that component. So once you have drawn the composition lines, you identified the intersection point of those three components. That point represents the specific unique phase composition of the mixture.
Okay, so for number 3, what is binodal curve or binodal? What does it imply in the diagram? A binodal curve is a line on a phase diagram that separates a single phase region from two phase regions, indicating the specific compositions where two distinct phases can coexist in equilibrium. In a diagram, the binodal curve shows the condition like temperature and composition under which a mixture will separate into two different phases. So for number 4, based on your constructed diagram, will a mixture contain 7% alcohol, 20% water, and 10% camphor remain clear or form two phases? A mixture of 70% alcohol, 20% water, and 10% camphor will likely remain clear in one phase since camphor dissolves well in an alcohol.
So for the conclusion, the experiment successfully determined the phase boundaries at the camphor, alcohol, and water system. The 6 experimental data points were plotted on the ternary phase diagram, and a binodal curve was constructed to connect these points, separating the system into a miscible one-phase region and an immiscible two-phase region. The results demonstrated that alcohol acts as a co-solvent, significantly increasing the miscibility of the poorly water-soluble camphor within the system. Mixtures falling within the single-phase region represent clear, stable solutions such as elixirs or spirits. That would be all. Thank you.